In the last part of the video, which I highly recommend watching if you haven't, we left off at the sun's helium flash. So, just to recap, when the temperature in the sun's core at the final red giant stage reaches 100 million Kelvin, a helium flash will occur, and the thermonuclear reaction of helium burning with carbon will begin. The sun, having gained a new energy source, will then shrink in size. This will happen in about 6.75 billion years, during the era when the sun's core abruptly ignites its helium. This will temporarily stabilize the sun and create a relative equilibrium within the solar system. In another 6.75 billion years, the sun's age will reach approximately 11.35 billion years. Its mass will not change after the red giant stage, but its radius will then shrink down to 15 solar radii. The surface temperature will be over 4000 Kelvin and luminosity will drop to 54 solar units. At this stage of the sun, as we can see, this is its habitable zone. Yes, the green zone has shifted significantly closer to it, but the inner rocky planets, especially Venus and Earth, are now in the unstable black zone, while Mars is just on the very edge. In the green zone, roughly speaking, Jupiter is located right here, and Saturn is also in the green zone during parts of its orbit. Time has passed, the climate on the planets and moons has stabilized, and here you see our planet Earth. This is how it looks in this era, a completely lifeless world, entirely desert, with no water and no atmosphere whatsoever. The average temperature is 217 degrees Celsius, with a maximum of 321 at the equator. From Earth's surface, the sun appears this large in the sky. The moon is in a similar situation, though it's a bit warmer here. The average temperature is 345 degrees Celsius. Now Venus without its atmosphere. Its average temperature is actually lower even though it's closer to the sun, at 180 degrees Celsius. Well, it's likely due to the average albedo because the simulator doesn't adjust it automatically here, and it's quite high. If it were properly adjusted, the temperature on Venus would have to be even higher than before. Mars has a similar temperature to Venus. The average temperature is 176 degrees Celsius, and Mars still retains a thin atmosphere, which consists mostly of carbon dioxide. From the surface of Mars, the sun looks like this. Now for Jupiter's moons, and here on your screens is Io. Its average temperature is minus 64 degrees Celsius. The temperature values are below zero everywhere, hiding the atmosphere and clouds. We can see that Io has quite a few sulfur dioxide oceans. The red bodies of water are clearly visible. There is this kind of desert land. We can even see ice caps at the poles. The next moon, Europa, looks like this. Its average temperature is minus 75 degrees Celsius. There is no atmosphere here. Now you see Ganymede. Its average temperature is minus 48 degrees, and it also has no atmosphere. And Callisto. Callisto has a dense atmosphere, an average temperature of minus 41 degrees, and a surface pressure of 0.56 atmospheres. Hiding the atmosphere and clouds now, let's see what's on the surface. Here, almost the entire moon is covered by a sulfur dioxide ocean. This looks really unusually cool, and there are many different island archipelagos, but unfortunately they are entirely lifeless, just desert. Polar caps are visible at the poles, and so such an unusual world. I'll descend to the surface. In Universe Sandbox, this is how it looks on the surface. If you try to look at the sun, something like this happens here. Some kind of strange circle, but it's definitely not Jupiter. Well, basically, a dense atmosphere through which you can't see the star. Now for Enceladus, it has changed. We can already see that the atmosphere on it has become very thin. The average temperature is minus 143 degrees Celsius. It's cooled down quite a bit. And Titan, of course, we see that it has no atmosphere. It hasn't returned. The average temperature is minus 105 degrees Celsius. A very cold, atmosphere-less, airless object. On Uranus's moon Titania, nothing special either. No atmosphere and the average temperature is minus 157 degrees. But on Triton, Neptune's largest moon, although the average temperature is minus 183 degrees, it has, as we can see, some kind of dense atmosphere made of nitrogen, I assume. If we hide the atmosphere and clouds, we see something interesting here in the southern hemisphere, and I assume in the northern one too. No, not in the northern one. I assume this is the part currently facing the star. Something interesting is happening here. In the specifications, the atmosphere on Triton consists mainly of nitrogen. The pressure here is over 3 Earth atmospheres, plus some traces of carbon dioxide and methane. And this liquid that we apparently saw here, let me hide the atmosphere and clouds again. This liquid I assume consists of nitrogen. If I turn off the liquid view here, then yes, you see it disappears, turn it on, it returns. So liquid nitrogen is present at Triton's south pole. On the dwarf planet Pluto, it's something similar to Triton. The average temperature is low, minus 181 degrees Celsius. And by hiding the atmosphere and clouds, we see the same picture as during the red giant phase. There's just an atmosphere, but I don't see any changes on the surface. I don't observe any changes at the poles either. There are no liquids here, unlike on Triton. Next, let's fast forward approximately 7.5 billion years to the transformative era of the Sun on the Asymptotic Giant Branch, AGB, when the star begins to undergo thermal pulses and the solar system enters the final, extremely dynamic stages of its evolution. Millions of years later, when the helium reserves are exhausted, the violent expansion of the star's outer shells will repeat and it will move to the Asymptotic Giant Branch, becoming unstable, constantly expanding and contracting as if breathing, becoming a Mira-type variable star. In 7.5 billion years, the Sun's age will be approximately 12.1 billion years. This will be the AGB stage. And now I'll show you how I'll transform the Sun to this stage. At the AGB stage, the Sun's mass will decrease further and the orbits will move away. The Sun's mass won't drop that much. I'm going to begin the reduction. Take a look. The orbits immediately start moving away. The Sun's mass should decrease down to approximately 0.65 of its original mass. I'm bringing it to this value, exactly 0.65 solar masses. We see that the orbits have shifted and become even further from the star, but with the loss of mass, the radius will also increase. Now I'm going to show you roughly how this process is going to take place. So basically I need to increase the star just like this. It'll expand to about here, then shrink, then start expanding again, and it's going to behave with these pulsations throughout this whole period. Anyway, I'll show you roughly, well, how it's going to look. Indeed, it is true that Venus will be swallowed up under those circumstances, and the overall radius should expand to reach approximately 1.25 astronomical units. Next, I'll adjust the temperature. The temperature of this star will be about 3100 kelvins, and its luminosity will be exactly 5,000 suns, roughly. And just look at what we ended up with. Earth in this simulation wasn't swallowed, it survived, but here it passes right very close to the Sun. Well, there are active debates now about whether Earth will be swallowed at this stage of the Sun or not, but as we can see, the simulator decided to save Earth in this situation. In terms of the habitable zone, what do we see? We even have Saturn ending up in the black zone here. Wow. Uranus is in the red zone, Neptune is in the red zone, even at the furthest point of its orbit, it's in the red zone. Pluto, as we can see, is in the green zone. We see Sedna here in this spot. For some reason its orbit isn't being drawn, maybe it's already leaving the solar system. The Sun's gravity isn't holding it anymore. I fast forwarded a decent amount of time. The climate has finally stabilized, and I stopped at the exact moment when Earth is closest to the Sun. And this is how our beautiful Earth looks next to this massive Sun. Everything on its surface is extremely hot. We see just a massive star in the sky that covers absolutely everything. Oh, sorry for blinding you, but I'll set it to informative mode here. It'll be easier on the eyes, and we'll be able to appreciate the scale. Just look at that, damn, everything here is incredibly close. And the molten Earth against this backdrop. And we see that only the part of Earth facing away from the star, where we have eternal night, isn't as molten. The average temperature on such an Earth is almost 1500 degrees Celsius. The Moon satellite is still orbiting here. Let's look at it. It's also very hot, just like Earth. The average temperature is also almost 1500 degrees Celsius. Now you see Mars. It's also burning, gradually losing its matter, and only on one of the poles that isn't lit by the Sun. We currently don't have a molten surface. The average temperature on Mars is about 1100 degrees Celsius. Jupiter has a temperature of 436 degrees Celsius. Its moon Io, here it is with a dense atmosphere. The average temperature is 381 degrees, hiding the atmosphere clouds, and the surface is without much change. I don't see anything special at the poles here either. Only on the South Pole we see a small area of liquid sulfur dioxide. On Io, the atmospheric pressure is almost 4 atmospheres. Europa is unchanged. It didn't gain an atmosphere. It just warmed up to 338 degrees on average. Ganymede also doesn't have an atmosphere. The average temperature is 442 degrees. If you gaze upon the dark side, you can see glowing molten rock on it. And here we see Jupiter on the left and the Sun on the right, which is much larger in size than Jupiter from its orbit. And this is Callisto. Callisto is actively losing its matter and most likely losing its atmosphere. On Callisto, the average temperature is 470 degrees Celsius, and the atmospheric pressure is almost 7 atmospheres. I'm hiding the atmosphere and clouds, and we see this kind of terrain. There's no liquid sulfur dioxide here anymore. We only see molten rock on the surface. I don't see anything at the poles either, except for the southern hemisphere. There's a small area of liquid sulfur dioxide here, and again, the atmosphere is so thick that the stars aren't visible at all. Next is the planet Saturn, where the average temperature is 314 degrees Celsius. And now you see Enceladus, and it has regained an atmosphere. The average temperature on it has warmed up to 210 degrees Celsius, but there are places where we have negative temperature values. The atmosphere consists of water vapor, and the surface pressure is 0.13 atmospheres. I'm hiding the atmosphere and clouds, and again, as with the red giant stage, we see liquid bodies of water on Enceladus. And as we know, where there is liquid water, life is also possible. But in the simulator, in this situation, situation, there is no life on Enceladus. As for Titan, which humanity is counting on for the future, there's no atmosphere here at all. The average temperature is 324 degrees Celsius. And here's something interesting, guys. At this moment in time, Neptune is actually closer to the Sun than Uranus, due to changes in their orbits. So, in this case, we'll look at Neptune first. This is what Neptune looks like. It's taken on such an interesting look, as if it's even changed color. The average temperature on it is 52 degrees Celsius, and its moon Triton. This is how it looks. It doesn't seem to have changed in appearance. The average temperature is minus 32 degrees. I'm hiding the atmosphere and clouds. Oh, now this is interesting. Look at how much water we have here on the southern part of the moon. In the north, everything is frozen, but even at the equator, there are areas with liquid water. I hope that's definitely liquid water. Yes, it actually is. The ocean is mostly dominated by liquid water, and the atmosphere is mainly nitrogen, and I see the methane concentration in the atmosphere has increased. Besides those elements, there's also water vapor and carbon dioxide. But unfortunately, life hasn't formed here. There's no vegetation anywhere. Also, the surface pressure on Triton is almost 8 atmospheres. I've decided to descend to the surface. This is how everything looks here on Triton. If you try to see the star, we again see some kind of black silhouette, and it's as if the sun is shining through there. For some reason, Universe Sandbox displays it like this graphically. It's strange. Well, overall, Triton has piqued my interest in this case. There's liquid water there now, which is already interesting. It's time to visit Uranus. On Uranus, the average temperature is 41 degrees, and its moon Titania has an average temperature of 46 degrees Celsius. As we can see, it hasn't acquired an atmosphere. And now, the dwarf planet Pluto. We see that it's losing matter. Evaporation of substances is occurring. The atmosphere is very similar to Triton's. The average temperature is minus 65 degrees Celsius, but there are places where the temperature is 60 degrees above zero, and the pressure is almost 5 atmospheres. And the most interesting part is to look at its surface. Oh, we have liquid water here too. This is at one of the poles. What about the other pole? There's completely nothing here. I take it this is the pole where the sunlight is hitting this part all the time. And we see islands, and on these islands, unfortunately, there is no life. Well, yeah, it really looks a lot like Triton, even with the atmosphere, which mostly consists of nitrogen. So here is the catch, guys. There is more liquid nitrogen here than water in the liquid reservoirs. So it turns out not everything is as similar as on Triton. And I will also show you the dwarf planet Eris. The average temperature on it is 13 degrees Celsius. There is no atmosphere here, just a heated object like this. Let's check the other dwarf planets too, and believe me, there is nothing special about them. The situation there is similar to Eris. Next, let's jump 7.85 billion years forward into the solar system after the sun completes all its giant stages and turns into a white dwarf. The sun's mass is not enough for its evolution to end in a supernova explosion. After the sun finally passes through its expansive red giant phase, thermal pulsations will lead to its outer shell being stripped away, forming a planetary nebula. In the center of this nebula, a white dwarf formed from the sun's core will remain, a very hot and dense object, comparable in size to the planet Earth. Initially, this white dwarf will have a temperature of up to 200,000 kelvins. At the initial stage, it will cool down quickly, then it will cool very slowly for trillions of years, turning into a black dwarf. Note, at this particular point in time, black dwarfs have not yet come into existence, and in approximately 7.85 billion years, when the sun's age is about 12.45 billion years, the white dwarf will cool to 25,000 kelvins, and now I will turn such a huge sun into a white dwarf. When its outer shell is stripped away, its radius will become roughly like our Earth, but I will set the value to 1.1 Earths. And just like that, the sun will shrink sharply. Along with this, its mass will also decrease a bit. I will make the mass about 0.55 of the sun's mass. It will be something like that. And we see that the orbits are also moving further away. The simulator has sped up here. It is just making a huge temperature. So I told you that it would quickly cool down to 25,000 kelvins. I will set this value, and the luminosity turned out to be about 0.03 of the sun's luminosity. How tiny it is. And so you see how small the sun's habitable zone has become now. It is even very far from Earth's orbit, and up close this white dwarf looks like this. Fast forwarded time, Earth now looks like this. The temperature has dropped a lot, already minus 221 degrees Celsius, and it continues to drop little by little, but the situation is clear anyway. Everything will simply freeze. I descended to the surface of the Earth, and you can even see this white dwarf sun. There it is. On the moon, everything is similar. It has become very cold. On Mars, it is the same situation. We see that the objects are very dimly lit. Little light comes from the sun. We can only do this to see it brighter. Here is also Jupiter's moon Callisto. We see that its entire atmosphere, which was there, fell to the surface and froze. The average temperature is minus 191 degrees Celsius. If we make it brighter, it is just an icy moon like this. The situation there is clear. Where there was an atmosphere, it simply fell to the surface and froze. Now, what happens to the orbits of distant objects in the solar system should be interesting. I've sped up time in the simulator as much as it would let me. As we can see, these objects are orbiting the sun stably, yes, on altered orbits, but at least they aren't leaving the solar system, except for Sedna apparently, because the simulator doesn't even draw its orbit, and it's likely flying out of the solar system. In short, the simulator processed all these orbits, something like that. This could be the distant, far-off future of our solar system. If you enjoyed looking into the future with me, please support this video by giving it a like and leaving a thoughtful comment below. Thank you very much for watching.